video, I want to talk about the difference between the integral and the antiderivative. Now, we've talked about the antiderivative already in class, and I introduced that as an algebraic construct, essentially the opposite operation or the inverse operation in effect to taking the derivative. If you have a function and you take its derivative, and then you take the antiderivative of that derivative, you can reclaim the function up to a constant. That's what we talked about. The integral, while algebraically is done by taking an antiderivative, is actually a geometric construct, and what it represents is the area under a curve bounded between values. So if you look at this picture here, all right, there it is. Okay, if you look at this picture here, you've got a function, f of x, right here. We're bounding it on the x-axis between a and b, and the function bounded between these values in the x-axis produces a geometric structure, all right? A geometric structure that we can talk about the area for. And when you don't have a nice straight line geometric function that we have a formula for, you can still find the area, or you can estimate the area by splitting this area here that they're calling omega, this area here, into rectangles. And if we come down here and take a look at this next shot here, all right, we split the interval a to b up into these individual little areas here, and then you take those areas and you square them off into these rectangles. And notice how we can almost fill the entire area, it's little bits here that are not filled, with rectangles. This idea here is going to give us an estimate of the area under the curve, because we simply take the area of each rectangle. Now, I can do this in a couple of different ways. I can square off the rectangles so that they're all contained inside the function, in which case I'm going to get an estimate that's slightly smaller than the area under the curve, or I can square off the rectangles so that they are squared off outside the curve like this, in which case I'll get an area that is slightly more than the area under the curve. But what I get are essentially boundaries. Right? I can bound the area under the curve between a lower value, this one up here, and an upper value, this one right here. I could also do this by squaring off the rectangles so that the midpoint, they don't show it here, but so that the midpoint of each rectangle is what's touching the curve. It doesn't matter. Either any way you look at it, you're getting essentially an estimate of the area under the curve. Now, if I do this to its limit, I take each rectangle, right, and each time I slice up the curve, I slice it up with smaller and smaller rectangles, and essentially allow the number of rectangles to go to infinity, then I have a process by which I can find the actual area under the curve. And what we do for that is, we do it by a formula, of course. All right, you calculate the number of rectangles you're going to have, that's your n here, over the width of the interval, so b minus a. All right, and that ends up being the width of your rectangles. All right, so if we let n go to infinity, all right, then we have the entire solid area under the curve filled in. Okay, and by summing those up, we get the area under the curve. So this ends up being our definition for the definite integral. Okay. If you read through section 6.3 in your textbook, there's a bit of an explanation of this. This website is good. It goes into more detail than you need, so if you want to read through it, you can. I was using it mostly for the pictures. But so the definite integral ends up being the sum. Is this the right one? No, yeah, here we go. All right, so the definite integral, which this is our notation. We use the antiderivative notation, the function dx, a to b. All right, so our boundary is lower bound, upper bound. and then it's the limit as n goes to infinity, and then we sum. If you haven't seen it before, this capital sigma means sum. 1 to n, f evaluated at the x, the point of each rectangle that touches the function, times delta x, which is the length of each rectangle, or the width of each rectangle technically. Okay? And when we do that, we get the area under the curve, and that's what we're defining as the definite integral. All right, I will continue this video in part 2.